To start, press any key. Where's the any key? I see esc, catarrh, and pigup. There doesn't seem to be any key.
Properties from algebra are basically reasons that can be used to justify statements that are being made about algebraic expressions. So you're probably familiar from a question such as this, solving for a value for x, solving equations from algebra, where you'd be given this statement and you go through making a sequence of statements until you arrive at the solution, which is a statement that x is equal to 2. Now what you didn't do in algebra is justify each of these statements in basically your argument here. So we're going to go through what those justifications are and how to use them in a more formal argument. So we have the addition property of equality, which is described here, but let's look at an example to get a more concrete idea of what it's saying. Given two sets of equations, I can add the right-hand sides of those equations, and it will be equal to the sum of the left-hand side of those equations. So like this, I can add my left-hand sides together, and it will be equal to the sum of the right-hand sides, which give me a process for making conclusions about what the sum of x plus y would be equal to. The subtraction property of equality is kind of like the cousin to the addition property, which is given the same set of equations, I could also subtract them from each other. So that's the statement that would be used to justify why you can subtract a set of equations from each other. The multiplication property of equality is the same kind of idea. Given a statement about x, I can take any number that's equal to itself, multiply both sides of that equation by that same number, and the result will be equal as well. The division property, same basic idea. Given a statement, I can divide both sides of that equation by the same number, and the result will also be equivalent. The substitution property, slightly different. I'm not really doing an operation in this case. It's basically saying that given two sets of equations, I can replace one value in one of the equations with a value described in the other equation. So given x is 3 and y is equal to x plus 5, I can replace x with that value 3 from the first equation and get a value for y. So whenever you're replacing a value with another value, that's a substitution. It's the substitution property. The remaining three you may not be as familiar with as the others, or they may not be as intuitive. The reflexive property says that any object is equivalent to itself. So that would be as basic as the number 3 being the same as the number 3, or in terms of congruence, the segment AD being the same as itself, segment AB. So these last three properties are not just properties of equality, they're also properties of congruence. If it helps, see the reflexive part of the reflexive property, like reflection. If you imagine a little mirror across the equal sign, it should be reflected equivalently on both sides. That's the reflexive property. Similarly for the congruent side, AB and AB are the same. So those are reflexive. The symmetric property says that the order of an equality doesn't matter. So the equality is symmetric, meaning that if x was equal to 3, then I could say the same thing, that 3 is equal to x. So I could write it in either order. The order of an equation doesn't matter, and similarly the order of a congruent statement does not matter. Angle 1 being congruent to angle 3 implies that angle 3 is also congruent to angle 1. The transitive property is saying that if A equals B and B equals C, then A equals C. This should remind you of our chain rule from logic, and it's basically the chain rule for algebraic expressions. If x equals y and y equals 4, then I can conclude that x equals 4. So it's kind of like links in a chain, and if it helps to think about those links in a chain, you can actually write it out as if x equals y and y is in turn equal to 4, then I can simply say x equals 4. So that's what the transitive property is doing. Rather than writing out a string of equations, I can write it as the first thing is equal to the last thing. Okay, so now let's look at how we're going to use these properties to justify that argument we just made. So looking at that sequence of steps that we described before we looked at those properties, I want to justify each of these steps using those properties of algebra. And whenever we're justifying an argument in our course, What we like to do is make it as clear, concise, and justified as possible. So to make it more clear, I'm going to add line numbers, and also I'm going to organize it into statements and reasons. This is basically our basic two-column format for proof. Now the first statement, you recall, was given to me. Knowing this, I want to arrive at a certainty that x has to be equal to 2 and justify each of those steps. If you look at what's happening in the first line to the second line, what I'm doing to get rid of that denominator is multiplying both sides of this equation by 5, and what allows me to do that is the multiplication property of equality, which you can abbreviate this way. Step 3 is less obvious. I'm looking at step 3 and looking at steps 1 and 2, and I don't really see where it's coming from. It wasn't a piece of given information, so it couldn't have come from there, but remember that if you have an equation which is mirroring itself on either side of the equation, that's the reflexive property of equality, which you can abbreviate reflex prop. Now the reason I bring that in is because I'm going to make it more clear to my reader exactly what I'm doing to get to step 4. So what I'm doing to get to step 4 is I'm basically taking the equation from line 2 and I'm subtracting the equation in line 3 to get the equation in line 4. Now why am I, or how is that working? Well, let's see, like 5x minus 2x is what's giving me the 3x, and then 2x minus 2x, those 2x's will cancel out and leave me with, that's 6. So that's the subtraction property of equality when I subtract one equation from another, subtraction property of equality. That's the whole reason I mentioned this reflexive argument in step 3, is so that I could more clearly demonstrate that subtraction and arrive at this conclusion. Finally, from step 4 to step 5, it should be pretty clear that to get x by itself, I need to divide both sides by 3. So I'm using the division property of equality, dividing both sides by 3, and I arrive at my final solution. So now I've justified my argument using those properties of algebra to my reader. You can also use these properties in a geometric proof, such as this. Given that ST is equal to Rn, so ST, this entire length segment, is equal to Rn, this entire length segment, and also IT is equal to Ru, so this tiny segment and this tiny segment. Now one tip I would suggest is that when you have small segments that you can easily label as congruent, I would do that to visually represent that information in my diagram. So now I can see that information without having to go back to this given. So if I'm going to justify each of the steps in this argument, I start with ST is equal to Rn. That was one of my given pieces of information. And then I'm making a statement about the sum of SI plus IT. Well, notice SI plus IT would form this entire segment ST, and RU plus UN would give me this entire segment RN. And this is that segment addition postulate that we talked about in class. The length of one segment is equal to the sum of its component segments. So the component segments of ST are SI and IT. I put them together, I have the entire length ST. So then looking at this, I'm looking at step 3, and it's not 100% clear where it's coming from, but if you notice that I originally had, the place that I see SI plus IT is right here, and I know that's equal to ST, which also showed up in this equation. I also have RU plus UN, which showed up as RN, which also showed up in this equation. So I'm basically substituting the equivalent value SI plus IT for ST and the equivalent value RU plus UN for RN, and I'm getting this new equation. Well, the property that allows me to do this is the substitution property of equality, which you can abbreviate substitution prop or subst prop. So once I have that, I now understand where this line came from. So now I'm going to look at 4 and try to figure out, well, where did that come from? It doesn't seem to have come from any of the lines above it. And if you ever get stuck trying to figure out where a statement came from, go back and look at your givens again. And in fact, that statement was given to me. So if you're stuck trying to justify an argument and you can't come up with a reason, double check that it's not a given, or if it is a given. So this one was actually a given piece of information. And why it's useful is, if you notice, especially the way that I wrote it, IT and RU and line up with those portions of this equation, and my goal was to prove SI equals UN. Well, if I subtract line 4 from line 3, the ITs will cancel out, and the RUs will cancel out, and I'm left with exactly what I was trying to prove. So how I'm able to get from these two lines to this line is subtracting 4 from 3, and that's the subtraction property of equality. So that's an example of how you would see these properties of equality showing up as part of a geometric argument.